Hey everyone, and welcome back to The Explainer. I am absolutely pumped to dive into today's topic with you. We're going on a bit of a trip into the hidden mechanics of our physical world to talk about vibrations and waves. Now, I know that sounds like we're just cracking open a physics textbook, but stick with me. Once you really grasp how this invisible transfer of energy actually works, you are going to look at literally everything completely differently, from a ripple in a puddle to the bass at your favorite concert. It's fascinating stuff, so let's just jump right in. Right off the bat, our source material throws us a bit of a curveball. It starts with this quote: "When there is a dream, there is a hope." Kind of a surprisingly poetic note to find in a physics text, right? But honestly, it totally nails the vibe of what we're looking at today. Because just like hopes and dreams are those invisible forces pushing us forward, waves and vibrations are the invisible physical forces pushing energy all across our universe. So here is the game plan for how we're going to build this up. 1. The power of oscillation. 2. Simple harmonic motion. 3. Waves, transferring energy. And 4. Progressive versus stationary waves. All right, let's get started with our first building block. Section 1, the power of oscillation. Okay, I want you to picture a spring, like a heavy-duty coiled metal spring. Imagine just pushing down on it with your hand, compressing it as hard as you can. While you're holding it there, the spring obviously isn't moving, but it is absolutely loaded with what physicists call elastic potential energy. It's essentially energy just waiting to happen, you know? That spring desperately wants to snap back to its normal shape, and the second you let go, it is going to unleash all that stored-up tension. So let's actually track how that happens step by step. Step 1, like we just said, the spring is holding all that potential energy. Step 2, you release it, and it expands, immediately applying a physical force. And step 3 is where the real magic happens. That stored potential energy instantly transforms into kinetic energy, the energy of actual motion. I mean, if you had a tennis ball sitting on top of that spring, it would absolutely go flying. And this core idea, energy shifting from potential to kinetic in a back and forth cycle, that is the absolute foundation of all vibrations. So we've seen one burst of energy. Now let's look at continuous cycles in section 2, simple harmonic motion. To really get a feel for this, our source outlines a pretty brilliant thought experiment. Picture an old-school record player, just spinning round and round at a totally constant speed. Now attach a ball right to the very outer edge of that turntable. Next, imagine shining a light straight at it from the side, so the spinning ball casts a shadow onto a flat wall behind it. For a second, completely ignore the turntable and just focus on that shadow. Check out what that shadow is actually doing. The ball itself is moving in a continuous 360-degree circle, right? But the shadow on the flat wall, it's just pacing back and forth, left to right, in this perfect, unbroken rhythm. It speeds up right as it crosses the center, and it slows down at the very edges before it turns around. This specific back and forth oscillation is basically the perfect visual for simple harmonic motion. It's incredibly consistent, and actually, it's the exact same mathematical rhythm a grandfather clock's pendulum makes when it swings. So what happens when that localized rhythmic energy breaks out into a wider medium? That brings us to section 3, waves, transferring energy. We've all seen this happen. Someone tosses a rock into a perfectly calm lake. Boom! That impact is your initial disturbance, and instantly you get these perfect rings of water expanding outward. It's such a classic visual of a propagating disturbance. But to really get what's going on, we have to look past the surface at the actual physics at play. Which leads us to the technical definition. Mechanical waves are a disturbance that travels through particles of a medium to transfer energy and momentum away from the source. It's pretty wild when you stop and think about it. The water ripples we just mentioned, the sound of my voice hitting your ears right now, or even the devastating seismic waves during an earthquake, they are all just mechanical waves carrying energy from point A to point B. And here is the absolute most mind-bending part of all this. The wave travels, sure, but the particles themselves, they do not. I really want to emphasize this because it changes how you see the world. The particles of the medium, the actual drops of water or the molecules of air, they simply oscillate around their equilibrium position. Basically, they just bob up and down or vibrate back and forth, handing off the energy to the particle next to them, like a giant bucket brigade. The energy cruises all the way across the lake, but the actual water molecules pretty much stay exactly where they started. It's wild. Now, because it relies on that bucket brigade action, mechanical waves have 3 hard and fast requirements. First, you need a source of disturbance, like dropping the rock. Second, you absolutely need a medium that can be disturbed, like the water. Drop a rock in the vacuum of space and you get absolutely nothing. And third, you need a mechanism to transfer that disturbance. The particles have to be able to physically interact with each other to pass that kinetic energy down the line. For our final piece of the puzzle today, let's look at how waves behave once they're out in the wild. Section 4, progressive versus stationary waves. Let's compare them, because the differences are night and day. A progressive wave is your standard everyday wave. The wave profile physically moves forward, it transmits energy from one place to another, and every single particle in the medium vibrates as it passes. But a stationary wave? Totally different story. The wave profile literally does not move. It transmits zero energy forward. And honestly, the craziest part is that there are specific spots on a stationary wave, called nodes, where the particles literally do not vibrate at all. They are dead still while the particles right next to them are going crazy. So how on earth does a wave just sit still? It's all about how they're created. A progressive wave is just a normal disturbance moving through a medium. But a stationary wave, which you might also hear called a standing wave, is created by the superposition of two waves moving in opposite directions. Basically, imagine two identical waves crashing head-on into each other. When they meet, they interfere. At those nodes we mentioned, the upward push of one wave perfectly cancels out the downward pull of the other, resulting in zero net movement. The wave gets trapped, bouncing in place, and completely fails to transmit any energy forward. Well, we have covered some serious ground today, all the way from the potential energy packed into a coiled spring to the crazy cancellation effect of stationary waves. So I want to wrap things up with a question for you to ponder. When you hear a sound across a room, what is actually moving? Based on what we just uncovered, you know the secret. The air molecules aren't shooting across the room into your ear. It is just an invisible wave of pure energy, bumping particle into particle in perfect harmonic rhythm all the way to you. It's just a beautiful way to think about the world. Thanks so much for hanging out with me for this explainer, and keep an eye out for all that hidden energy out there.